So I have a code, right? It could be, with ifs, and it could be, there is a general code. And I detect that here I access some pointer that I read here, right? I get this pointer here, right? This would be, the minute that I get it, it becomes hazardous. Because in the future, there may be an access to this pointer. So here I'm going to protect it, right? I'm going to say, I'm going to put a hazard pointer pointing to this pointer, to this address, and I'm going to verify that it hasn't yet been reclaimed, and now I'm going to have it. And if I, then I compare this pointer to something, then I'm going to keep this hazard pointer until I use this pointer the last time. After that, I can, release the hazard pointer and it can be reclaimed. But this is the way to go. I look at my program, I have some data structure, I have a code. I'm looking at all the hazard accesses. I look at the first time I get this pointer, which produced the hazard, and then after that I protect it, and I know I'm safe, and I can unprotect it, clear the hazard pointer after I've finished using it in my code. This is what I protect, and okay, so this is how I decide when I need to protect anything. Yes. I don't know if I have an example. I mean, I could produce an artificial, stupid example, right? That I look at and I don't need to protect. I could just not use what I'm looking at, right? I mean, I could use stupid example to answer. So the question was, whenever do I get a pointer and not need to protect it, right? So, and I could produce a stupid example where I get a pointer, but I don't really use it to any good purpose. But I think you're right that usually if you get a pointer and you're going to use it for a good purpose, you will need to protect it. Yes. Okay. So, so this is how to decide which pointers to protect, and rightfully, most times you get a pointer into the data structure, you will need to protect it. Okay. So the second thing is how do we verify that the pointer we protected has not been, just before we protected it, has not been reclaimed, right? And in general, what you do is you check that it's still reachable from the data structure and has the key that you wanted it to have. And this, you see, is becoming delicate. It really depends on your data structure. How do you decide if something has been unlinked, has been deleted from the data structure or not? Is really something that if you know your data structure, you will know. But automatically, it's not clear how you're going to check it. I mean, usually, if I have a queue, I know if something has been deleted or not. I can go from the head and check if it's reachable. If I have a linked list, I can also go from the head. But in general, if you have some strange data structure, I cannot automatically tell you how to verify. But this is something you have to look at when you install hazard pointer scheme into your data structure. Okay, so I decide what to protect, yes? Yeah, so if you're looking at reference counting, which I haven't defined or talked about, I'll talk in the second talk. Reference counting is like a generalization of that. Instead of saying I have something to protect, you're saying if anybody has any pointer to this object, then it's protected. And also, you don't only know that someone has an object, you also update how many have pointers to this. And yeah, it's similar. Yes, you keep a bit less information. You only keep indication if someone is interested in this object, and you don't count, how many pointers there are to this. Yes, but I agree. It's the basic idea is if someone is pointing to something, then you should not reclaim it, and reference counting is the same idea. Yeah. If you want to do reference counting in a concurrent setting, there will be problems. because of the races between, updating the counters and changing the pointers. I can talk to you offline because it will take time to explain these problems, but it will not be, if you want to put reference counting generally in a concurrent system, it's a very serious problem. It doesn't go smoothly at all. But to understand why it will take 10 minutes, I can do it in the break if you like. Okay, so the third thing was what happens if the verification fails. You install hazard pointers and you tell everybody, please do not reclaim this object. And now you check and you see that this object has been reclaimed. Now you're in the middle of a code of a data structure. You're traversing a list or something. And the memory manager failed. What do? Someone else wrote the code for the data structure, maybe. You now have to decide what to do. And again, this cannot be done automatically. You cannot say, here's what you do. In the original paper, they say, follow the path of the target algorithm when conflict is detected. There's some, vague words that could be interpreted in various ways. What really has to happen is you have to understand how you go back to the beginning of the operation without causing any harm. In theory, this will not work because maybe you've written something to shared objects and maybe you've ruined everything and stuff. You don't know what to do. In practice, it never happens. So if you look at data structure and you fail to protect a node with a hazard pointer and someone reclaimed it and you could not do anything, there is always a way to go back and start the operation from scratch. In practice, in all data structures that we know. But in general, it could be, if you look, theoretically, you could construct a data structure where it would really be a problem. But it doesn't happen in reality. So, okay. So, in real life, I would say also that we also need a memory fence. This thing, I have to make sure that other threads see that I protect a node before I actually touch it. This is very important. I cannot, install this hazard pointer, but let other threads see that I first touch this node and then install the hazard pointers. The order is very important. I first protect it, I verify, and then I touch this object. And this is costly. You see, I add here a memory fence after I install the hazard pointers, and only then I continue. This, if I read a linked list, and for each node that I traverse, I install a hazard pointer, which I should, then this is the most costly thing. This memory fence, for each read of a node, I have to put a memory fence. This is very costly. This is going to be the thing that will kill this method in practice, will make it too inefficient. And of course, if you have a hash function where you just touch the object, there's one memory fence, and this is not as bad. It may be as good as epochs. Okay, so this is really costly. The verification is algorithmic dependent, and you really have to understand the data structure in order to do it. The fact that you have to restart needs some structure of the code. You need to understand how you go back if there is a problem, which is a delicate point. And if you remember wait freedom means that you don't have to ever wait for any other threads. Even if you get me an algorithm that's wait-free, so I have a method that will always finish within a few steps, I put this memory scheme in, and it's not wait-free anymore, because here I have a test that can fail, and then I have to start from scratch. And it can fail forever. Other threads will proceed, and it's log-free, it's fine. Some thread will make progress, but I can always fail. I will try to protect this node. I will not make it. Someone will reclaim it. And then I will traverse the list again. There will be a new node. I will try to protect it. I will fail because someone reclaims it. It will not be wait-free anymore. So if you take a wait-free method, you add hazard pointers, it's not wait-free anymore. This is something that's not so good. Yes? Okay, so the question is what happens if I install a hazard pointer and die? Not me specifically, right? The thread, yes, okay. So what happens is that you lose space in the heap. So, and there is a discussion about that in the original paper. They say how many space is going to be lost in the heap because of these hazard pointers, because you protect stuff and that cannot be reclaimed anymore. And now threads start to die and all these protected places cannot be reclaimed anymore. So threads can still go on, but there is a limited space in the heap that cannot be reclaimed. So if you have for each thread 4 hazard pointers, then you know overall you're protecting 40 objects. If you have something larger for skip list, you may need log of n hazard pointers, and then you're going to lose that in the heap. But if a thread dies with hazard pointers protecting stuff, then there is a problem. Yeah, there is. You lose some space, but everything can go on and everything will be correct. You just lose some space in the heap. Okay. In practice, you don't lose too much space, and in practice, threads do not die, so everything is okay. Okay, so now let's go back to this delicate point about what unlinking mean. So previously, unlinking meant that if you unlink a node from the data structure and then a new operation starts, this new operation will not be able to see this node that has been unlinked. But here, it's getting to be a lot more gentle. So after unlinking, you want to make sure that no one can access this anymore, right? Because if you unlink, you put it in this retired list of objects that you've unlinked, and then someone can come and reclaim it if there's no hazard pointer to it, right? So no way you want to let someone get to it after it has been unlinked. Okay, so immediately as it unlinked, no one should get to it. This sounds reasonable, right? In a linked list, if you unlink someone and someone goes on, he will not be able to access it. If he's there, he's already seen it before and should have protected it with a hazard pointer. Don't remember if I have, yes, I have here a picture. So this is a bad scenario for this method. This is a scenario where the hazard pointer methods cannot be used. Okay, so what happens here is I have in the linked list 2 nodes that have been concurrently deleted, and they've been marked, if you remember from the talk by Danny. And then there was, like this guy has been changed to directly point to 15, and these nodes are still looking at each other. This is a really bad scenario for hazard pointers, because what happens here, suppose this guy looks at this and he has protected it with a hazard pointer, or, you know, tried to protect it, but now he's going to see that it's not. But in any case, suppose he's protected it and he can now go on and look at this thing. This is really bad. This is not protected by a hazard pointer. This is not going to be reclaimed. It has been unlinked, it has been retired, but this cannot be reclaimed. However, this guy is not protected by a hazard pointer. The 12 can be reclaimed. And this T2, the thread 2, that is now looking at 10 and protecting it, no one reclaims 10, no one reclaims 10, no one is reclaiming 10, but someone is reclaiming 12. So this T2 may go to 12. And this is going to be then broken, because 12 can be anything now if it has been reclaimed. So the hazard pointer method has a really important property for the unlinked. If something is unlinked, it cannot be reached. Here, it can be reached. And this is the way that Harris, so this linked list that Danny told you about was first introduced by Tim Harris in 2001. And then Maged Michael, when he suggested hazard pointers, he said, you know, I cannot work with this list and I'm going to change it. So this scenario never happened. So for Maged Michael, if you delete an object, you'll never delete 2 at the same time. You're going to return to the beginning of the list, and you're going to make sure one object is going to be deleted, and then you're going to return to the beginning of the list. If there are 2 concurrent nodes to delete, you will not delete them like this, because this cannot be used with hazard pointers. Okay, so Maged Michael actually had to take Tim Harris's linked list and change it to the worse, I will say. This the linked list that Maged Michael created was less efficient than the original list of Tim Harris, but it was possible to install hazard pointers with it. So we got memory management, but we got a not as good algorithm and overhead for each, traversal. Okay, so it is really tricky to tell if an algorithm unlinks node. You see, this is like a very strange scenario where two objects are deleted concurrently, and this scenario is created where it's bad for the hazard pointer algorithm. You have to know in your data structure or any data structures that you installed hazard pointer into, you have to know if something like that could happen. And this is tricky. This is not something you could take, so you cannot do automatically, and you cannot take someone who doesn't understand the data structure and trust him to tell if the unlinking is good. So, and it's not good when things are tricky. If you are installing something into your data structure, you don't want stuff to be tricky. You want them to be easy to install. So the linked list of Harris, and there is in the book of Erez Petrank, there is another linked list. They do not work with hazard pointers. You cannot install hazard pointers with them. They're fast, they're good, but you cannot reclaim memory with them in this manner, in a lock-free manner. So Maged list was slower, but you could reclaim nodes with it. Okay, and so sometimes you need to modify the algorithm to make it work, and that's not so good. You remember for the epoch thing, you just declare your epoch in the beginning, you declare your idle at the end, and you're done, and everything works. This is really easy to install, but it was not lock-free. Here, you need to do a lot of work to install hazard pointers, but it is lock-free. So you get lock freedom, but it's not easy to install. Okay, so questions on this hazard pointer scheme? Okay. To summarize the basic methods, we have two basic methods from the beginning of the 2000s. Harris, when he produced his linked list, he said, let's do epoch-based stuff. It's very easy, it's very fast, but it's not lock-free. If a thread crashes, you're dead. You cannot reclaim memory. And hazard pointers, which were introduced a year or two later by Maged Michael, was inefficient. Whenever you walk through a list, you have to, each time, declare, please do not reclaim my memory. You have to put a fence, a memory fence, which is really kills all your efficiency. We saw that it was not easy to implement and that it's not applicable to all algorithms. Okay, so it doesn't look very good, right? So we're not in a good shape here. Either you give up lock freedom or you give up an efficiency, and this was the state for many years, like I think maybe 2012, there was the next paper dealing with it, and now there's a lot of work on it. I see lots of papers coming, and I review grant proposals of people who want to work on this, so this is going to continue for many years now. People want to solve this. They want to have something simpler, and they want to have something that actually works efficiently. Maybe efficiently is first thing to do, and then hopefully get something simpler. So, challenges. Make it lock-free and inexpensive. We don't have that now, right? We don't have that in what I explained so far. And can we make application of hazard pointers automatic? That will also be very nice because it will not be that tricky to put it in. And can we run all lock-free algorithms? Because right now we're limited. Things that cannot unlink in a very strict, strong manner, that when you unlink a thing, no one will access it anymore in your algorithm. If you don't have that, you don't have hazard pointers. And the question is, can we do better? Can we have something that will run all algorithms and not just these specific algorithms with specific property that, it's very difficult to decide. Here is a few of the new schemes that have come out between 2013 and 2016. There are 8 schemes here. I think so. I don't want to go over them because I don't have much time. But in general, some of them, what they're trying, and actually you can see, so many of the speakers here have been involved. Dan, Alistar, who spoke yesterday, this is myself, this is a work by myself, this is another Alistar, this is with Maurice Hurley. So a lot of your speakers are trying to solve this, and it's still open. So what people here have been trying to do is basically to either make the epoch algorithm lock-free and partially succeed, or to make the hazard pointers more efficient and also partially succeed. So for example, some of these papers are really, they're saying, you know, the problem is that we have this, okay, so the problem is that we have this costly memory fence. And there were several papers that tried to get rid of this memory fence. And so a memory fence is used to make sure that everybody has seen that I protected stuff with the hazard pointers before I go on and touch the object. And so some papers have even said, let's wait enough time to make sure that the hazard pointer is seen. And then they suggested changes to the hardware that would make it possible to just wait and know, or to make all other threads spill their buffers and stuff like that. So this is one way people try to go. Another way that people try to go is for the epoch, to solve the epoch problem. So for the epoch problem is that when one thread is not responding, no one can make progress in reclaiming. And so there was one paper who said, so let's signal all the threads and make them wake up and respond. And so we'll have the epoch-based thing, which is very fast, also be lock-free. These are not the greatest solutions. So if you signal a thread today in systems, this would mean taking a lock. So you have to maybe change Linux to make it not get a lock. All these things are not, you know, it's not solved yet. That's what I want to say. And I'm going to skip this survey. And I want to talk about something which is not trying to, you know, improve these two methods, but is giving a new, there is something new about it, and I want you to look at it. I want to talk a bit about it. And this is the optimistic access. Okay, so the main idea is that you want to make the read. So, for example, if I traverse a linked list or a skip list, and then I get to a node and write something, most of what I do is read. I read and read and read and read. Eventually, I write something. So if I could make these reads not expensive with the hazard pointers, then I would be in a much better shape. So eventually, I will make one write, and then I will need to pay for the memory management. But reading, I really want to do fast. Okay, so how do I do it? Let's just not protect the reads, right? So it could be that I'm reading stuff and traversing a linked list, and the objects there are being reclaimed while I read them. This is not so good, but it's very fast, right? And so this is like reading optimistically. I say, I hope this will not be reclaimed, but it may be reclaimed while I read it. And this is kind of risky. So what I do is I validate. So I read, I go to the next object, I read, and then there will be a little flag, my own flag, that will tell me if anybody has reclaimed anything while I was reading. So I read, and then I check if there was reclamation. If there was a reclamation, I know that I'm dead, I need to start over. But if there was no reclamation, I can go really fast. So without reclamation, I don't need to protect anything. And reclamation happens very seldom. So I usually can go very fast and go to where I need. Read, 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 read. After each read, I check if a reclamation has happened. If a reclamation has happened, so what I read is useless. I don't know what it is. It could be any value because it has been reclaimed and may have been used again with different values. So I read, verify, read, verify, read, verify, read, verify. I do not tell anybody anything, and I don't do any memory fences. I just walk over the list like that. And then when I get to a write, then I will be a lot more careful. I will use a hazard pointer as the previous scheme. So the way to do it is that there is a reclamation flag that every thread has that tells him if a reclamation occurred. So before doing any reclamation, a reclaiming thread is going to set this flag for all the threads, so they will know there is a problem, and then he does the reclamation. But when there's no reclamation, all these threads are down, and threads can just go fast reading in the data structure and just worry about writing. So one thing we have to make sure is that there's no trap, right? If I read something and I read the wrong value, maybe there will be a trap because I touch stuff that has been returned to the operating system. In data structures, usually you don't return pages to the operating system. If you do, so just getting pages with the operating system involves getting a lock. So if you really want to do data, and people that do data structures do their own allocation in any case, but they should. So if you do your own allocation, there will be no trap. The traps happen when you touch something that is not, that you don't have by the operating system. And if you want to write, you use hazard pointers as before. Yes, question. A magical? So so what happens is so for each thread, there is a flag that tells him if there has been reclamation. I'm going over it, without getting into the details, but whatever you want, I can tell you. But so each guy has a flag telling him if there has been a reclamation. Now T1 goes over a list, right? So he traverses this list, he looks at this, he looks at this, he looks at this, and goes on forever. Then he has to change something. So for all these reads, he reads the next pointer and says, was there any reclamation? I check my bit, and then I go on. Was there a reclamation? I check my bit, and then I go on. This goes very fast because his bit is usually in his cache unless it's changing. And when he gets to the place that he needs to write or read, then if there has been no reclamation in between, he's just finished his operation very fast. So each thread has his local flag, but the reclamation procedure is before it starts reclaiming is going to set for all threads this flag so that they know a reclamation has happened. Sure. So you're suggesting that each object will have a counter that will tell how many times it has been reclaimed. Whenever you reclaim an object, you increase this counter, and everybody can tell if something changed in the object, if it has been reclaimed, because this counter has been increased. So all objects have this number, and if the number changes, so someone has to change this number for all the objects. This is basically a kind of virtual way to talk about this, right? Because you tell everybody that some reclamation has happened, and then they know they have to be careful with any value that they read. Which one looks like global? This one or the counter? Right. Right. So you're suggesting somewhere to be able to tell by the object if it has been reclaimed. We could look into that. I mean, there would be races that you will need to solve. It's not far away from this method, except that you will have per object flag instead of one flag per thread. This is the thing here is that it's very low cost to have a local flag where you can just read again and again to verify your reads, and it works very fast. I will try to show you measurements, and then you'll see it's very fast working. Yeah, if I can hear you. Right, good point. So someone has to reset the flag. So the reclamation says, to all threads, the reclamation says, now there is reclamation. And whenever a thread tries to read and sees that there has been reclamation, then he will reduce it, but he will wait until reclamation ends. Right? So it's going to be, I see that I read a bad value maybe because there has been reclamation while after I read this value or after my previous check. So there has been some reclamation. I don't know if this value is correct. I have to do something. I have to restart my operation, and I also have to reset this flag. But I will, before resetting it, I'm answering your next question already. Before resetting it, I will wait until the reclamation ends, so there will be no race between me and the reclamation that's happening concurrently. That's good? It's what? So either, no, it is lock-free, but you're right that if I wait for a reclamation to end, it will not be lock-free. It is lock-free, I'm sure. I have to think about it. I cannot answer immediately, but let's talk in the break. It is lock-free, I'm sure. But you're right, you raised the point that I cannot answer now. Okay, another question? Okay. Okay. So I just want to say that reading optimistically is something that has not been tried before in memory management in general. There is like a kind of a fear that if you reclaim an object, if you touch it again, bad things will happen, and this is really a good fear. And so no one has ever done it for any purpose. And here it is done for efficiency. And so for optimistic access, what you get is a really small overhead on the reads. You basically check a local flag, which is really good. And then checking a flag is not something that you don't have to understand, the algorithm that you're working with very well. One of the problems we had with hazard pointers is that in order to verify that we are okay, we had to understand the algorithm and see that stuff has not been reclaimed. Here, you just check a flag. This is perfectly fine. Even when you protect something by a hazard pointer, you don't need to understand the algorithm. You just check this flag. So when you do install hazard pointers for writes, your validation is very, very easy. And you just check this local flag, and you're done. Restarting is still a problem, although in practice it is fine. You can restart, and it is really usually easy to just go to the beginning of the routine, start from scratch the operation when you fail, and everything works well. You have to be careful about that, and in theory you can build stuff that don't work, but this is something that you have to do. You're returning to some kind of a safe point, and what the paper about optimistic access did is to look at normalized. There is a definition of a normalized lock-free operation, and all of the lock-free data structures that are available today have a normalized form, And when you have a normalized form, you can restart automatically. It's very clear where you're going to restart. So if you do that, the structure is well done. Okay. Can you do optimistic writes? You cannot, because you're actually changing the data structure. You don't want to change stuff if it has been reclaimed. That's why you use hazard pointers. Okay, so let me jump one slide about evaluation. This is a linked list with many nodes, and what you see here is higher is better, and the hazard pointer is this thing really low here, below, and then above you can see if you use optimistic access, if you use no reclamation, so you don't spend any time on reclamation, or you use epoch-based reclamation, they're all excellent. So the epoch-based is not lock-free, and optimistic access is lock-free, and they're all acting, almost as if you don't reclaim memory at all. If you take hazard pointers, it's going to be a serious blow to your efficiency. And I'm going to jump over all of these. Okay, and I'm going to finish here because I want to finish in this first part, the manual reclamation. So this is the overall picture. There are papers trying to reduce the overhead for hazard pointers. There are papers that are trying to improve epoch-based. And there is this optimistic access that I just talked about that is not related to these two methods. Questions? Everything was very clear, or the other way around? Yes. Epoch-based, yes. Right. So if you control the scheduler, so theoretically lock-free algorithms say the scheduler behaves the worst that you can think of, and still you have progress. This is the definition, and this is what people try to obtain. But if you really have the system is yours, you're controlling the scheduler, you can really work out the operating system, and you can make sure that threads make progress all the time. Then things become better. For the epoch-based, I think it would solve the problem of being non-lock-free, yes. In general, it doesn't buy you lock freedom all the time, because when you run a compare and swap, you can fail because someone else has changed it, right? So you cannot, not in hardware, not in operating system, guarantee that the compare and swap will succeed. But for epoch-based, all you have to make sure is that all threads make progress, and that you can use an operating system to ensure that it happens. If if a thread is not doing something really horrible, like being stalled on something, but if a thread is executing your code and is idle, if it's not, is telling it's idle if it's not executing your code, then controlling the scheduler will be a solution to the epoch-based to make it lock-free under restricted scheduling. Yes. Yeah. Right. So the question is why do I put a flag for each thread, or is it important, or I could just use a global counter tells me how many reclamations happened, and then I could check it after each read and compare. This is just for efficiency. So what would happen if you did that? You would read, before you read a value, you'd read a global counter, and then you would read the value, and then you read the global counter again, and you would compare them, and all of that would take registers. I mean, if you look at what happens at the bottom of the computation, there's register allocation, which is extremely important to the how your thing runs, and there's also questions how much time. I mean, if you touch the cache or not. I mean, if you only touch your own local cache, or you have to go farther, and so having your local flag that you only check it, you don't read two values and compare them, and you don't touch some global thing, your own local cache, if you check that, it's a lot more efficient. We've actually used, we compared to this idea, we ran it and compared to it, and there was a serious difference. I mean, it was really useful to have your own local flag for efficiency only. The same correctness would work for this case too. Yeah. Okay, time for a break. Thank you.